This recording, we discuss what we refer to as free body diagram. Okay, now I'm going back. I'm not going to run the simulation here right now, but these are snapshots from what I did before. You notice here we have the cabinet and we are pushing on it. The applied force is represented by this blue arrow, and the friction force is represented by the red arrow. And then it is showing us here what it's calling the total force, and it is pointing towards the right. And actually, if we were running the simulation right now, we'll see that the cabinet would be accelerating in the same direction as that force. And the idea behind this, that's my unbalanced force. If we were going to apply Newton's second law of motion, we have to investigate all the forces acting on our cabinet. What are all the forces acting on it? In addition to this applied force and the friction force, there will be the gravitational force due to the Earth pulling down on it along the vertical, and there will be a normal force due to the floor pushing up on it from the bottom. So these are the two other forces acting on it. They are both along the vertical, along with these two forces along the horizontal. If we were to write Newton's second law that says the sum of all forces, remember the sigma here says sum of all external forces acting on the cabinet, in this case, is going to be equal to m times a. And it is going to be also called the total force, or the unbalanced force, or the net force, whatever you want to call it. Now, in this case, these forces are going to be Fg, the gravitational force, the normal force, Fn, plus the applied force, I'm going to just label it F sub A, plus the friction force, F sub F. The sum of all of these is equal to ma. And remember that these, if you notice here, these vectors are not along the same direction, so we cannot simply add them up. What we have to do is consider the vectors that are along the horizontal by themselves, and consider the vectors that are along the vertical by themselves. One thing to help us figure that out is what we call the free body diagram. That's the term, what we call the free body diagram. The way we do that, to simplify things, whatever we think of as forces acting on our object, we draw them by themselves in symbolic format using arrows without having to worry about drawing the object. Now, when we draw them somewhat like this, we can see distinctly what the forces are, and which forces are along the same direction, and which forces are perpendicular to that. For example, here we see that F sub n and F sub g, both of them are along the vertical, and both of these are along the horizontal. Now, F sub n and F sub g, we don't see any acceleration upwards or downwards, so that tells us that these two must be balanced. F sub n and F sub g, in this case, are balanced. And in this graph, in this diagram, we see them equal to each other. However, if we are noticing an acceleration along the horizontal, that would tell us that Fa and Ff are not balanced. And that's what we see here. Notice in the free body diagram, we don't have the net force or the total force drawn. Personally, I prefer it like that. We'll see in another simulation by the same group, they end up adding it. I don't like that. Why don't I like it? Because it might help the students think that what we call as the total force is an additional force acting on the object, which is not the case. What we call the total force is just the sum of what's in here already. So now here, Ff and Fa are in the same direction, but they are unbalanced. So Fa minus Ff is going to be my unbalanced force. It's Fa minus Ff because Fa is larger than Ff. Okay, let's look at another case. In this case here, the cabinet is moving, but I'm not pushing anymore. So what is it doing? What's going to happen to it? Since I'm not pushing anymore, it was moving, there is a friction force acting on it. So if we look at it in terms of a free body diagram, Fg and Fn are still along the vertical. They are not affected by the fact that I'm applying a force or not, since the force I'm applying is along the horizontal. So these two are still balanced. However, along the horizontal, we don't have any applied force anymore. We have only the friction force. And there is nothing to balance it. So my unbalanced force in this case, or my total force, is the same as the friction force. Now, since my motion is in this direction, and my unbalanced force is in the opposite direction, my cabinet is going to slow down and eventually come to a stop. Okay, now let's take another case. Okay, I'm going to run the simulation here so we can see what's going on. It's the same situation. We are going to have the same cabinets. The interface is slightly different, and there are more things to play with, to contend with, because the physics is a little bit more complicated. But what we have here is our cabinet on a ramp. And we have the person who's going to try to push it. Now, there are a few key points here that we need to pay attention to. First, before playing with the simulation, let's consider the forces acting on it. First, think of the gravitational force, which is in blue here. It is going to always be pointing towards the center of the Earth. It's not going to be pointing towards the ramp. It's going to point towards the center of the Earth. The gravitational force is due to the Earth, and the fact that we put the cabinet on a ramp is not going to change where the Earth is. So this one is going to point always along the vertical towards the center of the Earth. That's a key point. That's an important point. Now, the normal force, like we mentioned before, it's here in purple. It's always going to be perpendicular to the surface. This is my surface, perpendicular to it. That's what we see there in purple. Now, if we make a free body diagram, by the way, first, before we talk about the friction, now the gravitational force is along the vertical. The normal force is not along the vertical anymore. It's perpendicular to the ramp. So it has part of it is along the vertical and part of it is along the horizontal. It is acting along both directions. But it's not strictly along the vertical, while the gravitational force is strictly along the vertical. Now, if we draw a free body diagram, trying to draw the forces, so if we draw the vertical this way, the horizontal, whatever is perpendicular to the vertical, now you notice that my F sub n is not going to be along the vertical, like we expect it not to be. Now, when you focus on this a little bit, what you notice, F sub n does not balance. Let me retract that. Let me retract that and go to the simulation, just to ensure that we get this straight. Okay, here's the simulation. I'm going to rewind it. The nice feature that this one has slow motion. Oops. So this is what we have right now. The cabinet sitting on the ramp, not moving, not accelerating, nothing is happening to it. So what that tells us, it tells us that the forces must be balanced. All the forces together must be balanced In other words, we have no unbalanced force, no total force, no net force. Okay, let's go back to the presentation. Okay, so the forces are balanced. Now, so what's going to balance for us F sub g? What's going to balance it is going to be contributions from both these forces. Both of these forces are acting not along the horizontal, not along the vertical, along both the horizontal and the vertical. Each one of them is acting along both directions. Now, the red one, the friction force is going to act always parallel to the ramp. So it's going to act either up or down. Here we have it up. We'll have to discuss in a second why. But so we have that. It is acting parallel to the ramp, but that's not the horizontal. The ramp is making an angle with the horizontal. That's why we see it making an angle. So it's acting both horizontal and vertical. The normal force is also acting that way. Because of that, both of them are going to be able to help balance out F sub g along the vertical. Now, what about the horizontal? F sub g does not have any contribution along the horizontal. F sub n, however, has a small contribution along the horizontal. Now, since we don't have acceleration, that tells us that it must be balanced by something. What's balancing it in this case? It is the horizontal part of the friction force. That's why we know that the friction force is pointing up as opposed to down, because it's balancing that part of F sub n. Okay? This is one situation. Let's look at this other situation where we apply a force, but the force that we apply is not large. So we still have no acceleration. Our forces are still balanced. So it's the same situation as we had before, except now it's not very visible here, but we have two forces that are acting at an angle. Since the push is parallel to the incline as well, both forces are parallel to each other and pointing upwards. The rest is not changing, except now we know that what's going to balance F sub g is going to be part of F sub n and part of the applied force and part of the friction force. And what's going to balance F sub n along the horizontal is going to be part of F sub a and part of F sub f. Okay? Let's go on to another case, an even larger force. Now the story changes a little bit. If my force is large enough, and I still don't have motion, still don't have acceleration, I still don't have acceleration, my forces are still balanced, but something has to balance the excess force that's given by this. So what happens? The curious thing is, my static friction force is now pointing in the opposite direction. That's the main reason I did all of this. The static friction force, you cannot always easily predict its direction. You have to analyze the situation to try to figure out what's its direction. Now, of course, in this case, if we apply a large enough applied force, we are going to eventually get the cabinet to accelerate, and in that case, we get something like this. So my applied force and my friction force, eventually they are not going to balance out, so I'm going to have an acceleration along that direction. Now, this free body diagram is fine, but it's not really great or does not make the math easy for solving problems. Usually, we are not doing this complicated math in this course. I'm just mentioning it here. But usually we choose the free body diagram such that we choose the horizontal axis parallel to the ramp and the vertical axis perpendicular to the ramp. So then the story will worry about balancing some other way. Mathematically or physically, it's the same situation. Mathematically, the math is a little easier if we draw it the way I just drew it. Okay, let's go to the simulation and see what I was talking about. So we'll put it in slow motion. No applied force. So now we have 100 Newton applied force. So my friction force is still pointing that way. You can look here as well. Now 300 Newton applied force. Friction suddenly switched direction. 500 Newtons. And now we start having an acceleration. And we have a net force in the upward direction. That finishes this part about free body diagrams and ramps, normals, friction, and gravitational force. Several things we have seen here. Okay. We'll work some examples after that.